Lesson 951, One-Way ANOVA, Equal Sample Sizes. To this point, we have tested claims about means from one or two populations or treatments. The methods discussed so far do not allow comparisons of three or more means. In this lesson, we study analysis of variance, a test which allows the comparison of means from three or more samples. Analysis of variance is abbreviated ANOVA. In this lesson, we use ANOVA to compare means from three or more samples with a treatment applied to each at a single level. A level can be a dosage amount. With only one level applied to each sample, we are conducting one-way analysis of variance. One-way analysis of variance requires that our samples are drawn from normal populations with equal variances. Variance is the square of standard deviation, which we saw in Module 2. While these requirements are rarely satisfied, the test is robust. Off to the right, if a test is robust, that means that it tends to work well, even when the requirements are not met. Also, the test is greatly simplified if each sample has the same size. So this is how we will proceed. The term analysis of variance sounds intimidating, but don't worry. Variance is just the square of standard deviation. So if our standard deviation is 3, then the variance is 3 squared, which means you just multiply 3 times itself and you get 9. And the test compares two variances. So first, are there differences between pain relievers is going to be our example. An experiment was conducted to compare 5 treatments for reducing fever. 35 patients were randomly assigned into 5 treatment groups. The patients' temperatures were taken 2 hours after receiving the treatment and are given below. We will test the claim that there is no difference in mean body temperature among each of the 5 treatment groups using a 1% significance level. So notice we just started talking about a hypothesis test. So we are going to test the claim, and the claim is there is no difference in the mean body temperature among each of the 5 treatment groups, and our significance level is 1%. Because of the requirements for this test, we assume that independent samples were drawn from normal populations with equal variances. So on the next page, you can see the data. So here we can see the 5 treatment groups. These are the columns. The first column is placebo, second column is aspirin, third column is anisine, fourth column is Tylenol, and the fifth column on the right is bufferin. And if you notice, in each column there are 1, 2, 3, 4, 5, 6, 7 numbers. They took 35 people, they split them among 5 groups, so there's 7 people in each group, each getting a different treatment in each group. So number 1, work with your group to devise a strategy that could determine if there are significant differences between the means represented by these samples. So you can think about this, you can text with each other. Just think, what could you do to try to compare each of these groups? And then try to find out if there is a significant difference between the means represented by these samples. What might you want to do? You might want to think that in each group, if you are trying to determine if there are significant differences between the means, what might you want to find from each group is probably the mean. And then compare them. That would at least be an initial starting point. So for us, since we're conducting a hypothesis test, we go back to our 4 steps. Step 1 is determine the hypotheses. The hypotheses for analysis of variance are the null hypothesis H0 says mu1 equal mu2 equal ... equal mu k, which really means the mean value for each group is the same. That's what that null hypothesis says. The alternative hypothesis HA says at least one population or treatment mean is different. So symbolically, we have a way to represent the null hypothesis, but as a sentence or a phrase, you could also say all population means are equal. Whereas the alternative hypothesis really just has this statement. So for number 2, Give the null and alternative hypotheses using the correct number of means. This means that for our null hypothesis, just so you can understand how the symbols are being used above, we have 5 different treatment groups. So there's going to be 5 population means. So we would say mu sub 1 equal to mu sub 2 equal to mu sub 3 equal to mu sub 4 equal to mu sub 5. Whereas the alternative hypothesis, at least one of the population mean is different, we could say the same thing. So at least one of the means, meaning one of those 5 that we just listed, is different. We just need one of them to be different in the alternative hypothesis. So step 2, collect the data. One-way analysis of variance is a test which compares means from k different populations or treatments. When comparing populations, samples should be random and independent. When comparing experimental treatments, subjects should be randomly assigned to experimental groups. In this example, we are comparing means from k equal 5 different experimental treatments. Those are the 5 columns we have above, so in this case, k is equal to 5. When conducting one-way ANOVA with equal sample sizes, we will need a sample mean and variance, which again is the square of the standard deviation, from each of the k samples of size n. So again, just to reiterate what they're talking about here, k is the number of samples, whereas n is the sample size. So here we have 5 columns, so that's k, and then we have 7 people in each column, that's n. So turning the page to number 3, statistics for all treatments except Tylenol are given below. Compute and enter the values for Tylenol. Be sure to enter the square of the sample standard deviations to make them sample variances. Most values are rounded with one place more after the decimal when compared to the sample data. So if you go back to the previous page, you can see that your sample data is rounded to the first decimal place, whereas if you look at what they've written in these columns, the mean for placebo has 2 decimal places. The mean for aspirin, anisin, and bufferin all have 2 decimal places. And then we have S squared, that's the sample standard deviation squared, that gives us variance. And then you can also see the last row, n. Notice that 7 is the sample size for each of those. So we do know that for Tylenol there are 7 in that sample. And then you could just go back to your data, enter Tylenol into one list, and then use one variable statistics. So for number 3, use one variable statistics to find x bar and s squared for Tylenol. So when you do that, you're going to get the following things from one variable statistics. For the mean for Tylenol, I get x bar equal to 95.3. And then for the sample standard deviation, I get 1.106, but we need the sample standard deviation squared. So I'm actually going to write a couple more decimal places. That's what S is. And so then my sample variance would be taking that number and squaring it. 1.106044 squared, that gives me 1.223. So I entered those into my column, the mean 95.3 and the sample variance for Tylenol 1.223. All right, so number 4, in the image below, confidence intervals are depicted graphically for the mean temperature for each medication. Write a sentence or two describing what this tells you about the apparent differences between them. So they've done all of the confidence interval work. When you look at these images, you have two parentheses and then a vertical slash in the middle. And what you can think is for each, the vertical slash in the middle is the mean. And then we use our margin of error to build the confidence interval around that. What you might want to think when looking at this image, does it seem like one confidence interval is different from the others? What you might want to notice is there one of them that seems to be furthest away from the rest? And just from that thought, you can see that placebo, that confidence interval, seems to be different from the other. And with that thought, think of how that compares to your alternative hypothesis, where we wanted to see if one mean was different from the others. All right, step 3. Assess the evidence. As mentioned, one-way analysis of variance assumes that the k population variances are equal. The test statistic is the ratio of two different estimates of the common variance, which is sigma squared. The first estimate is called the variance between the samples, and the second is called the variance within the samples. So this ratio is given the symbol capital F as our test statistic, and that's equal to the ratio or fraction of those two variances. So we're about to walk through a whole bunch of formulas to see how this works, but at the end of this, we will get a calculator function that makes this much more easier. The first estimate of sigma squared uses the standard error of sample means. That's symbolized sigma sub x bar. That's the standard error of sample means, and that's equal to sigma divided by the square root of n. If we solve for sigma, meaning the symbol that's in the numerator of this fraction, and square the result, we end up with sigma squared equals n times sigma squared sub x bar. The variance, that's that symbol sigma squared sub x bar, is the squared standard error of all sample means from samples of size n. This can be estimated by the sample variance of the k sample means, which we denote as s squared sub x bar. Thus, the common population variance is estimated as sigma squared is approximately n times s squared sub x bar. The estimate of sigma squared is called the variance between the samples, because it uses the variance of sample means, s sub x bar squared, to measure the differences between the samples. So number 5, what is the variance between the samples? So we need to figure out this calculation. N, remember, is 7, and then s sub x bar squared. That means we need to look at the variance of our sample means. So if you go back to the previous page, you'll notice in number 3 we had 5 different sample means. So we'd have to take those 5 sample means, put them into a list, and then find the standard deviation and square them. So let's actually do that. So in my calculator in list 6, I'm going to type in the 5 sample means that we had. So 98.3, and then 96.2, and then 96.83, 95.3, and then 96.2. And then I will click Stat, and then calculate for one variable statistics. And I'm going to use list 6 for this. I don't need a frequency list. I just want to calculate. And you can see that capital SX is equal to 1.112106. That's again that standard deviation. So if I want to find the variance of the sample means, it means that I need to take that standard deviation, 1.112106, and I need to square that. So I'm just going to find out from my calculator, 1.112106 squared, and then I'll round that to 3 decimal places, and it gives me 1.237. So then the calculation that we're looking for to fill in the blank, that will be 7 times 1.237. So 7 times 1.237, and I get 8.659. So there's a lot to do in that. We had to calculate the variance of the sample means using a list. Then we had to multiply 7 times that variance, and that gave us our final answer of approximately 8.659. Another way to estimate the common population variance is to simply compute the mean of the individual sample variances. This mean is called the variance within the samples, denoted S sub p squared, because it uses the sample variances which measure variability of data values within each sample. The variance within the samples is also called a pooled variance. That's where the p comes from in the subscript, which explains its notation. So in this case, the approximation for sigma squared is approximately S sub p squared, which is equal to the sum of the sample variances, that's the sum of S squared, divided by k, which again is your number of samples. What is the variance within the samples? S sub p squared. Be careful, this is the mean of S squared values, so don't square the result. So this means that we go back to our table on the previous page where we had those S squared values, and we find the mean of those, which means let's just add those 5 numbers up in the row for S squared and then divide by 5. That's all that this calculation is. So if you go back to that table and you add up those numbers for S squared, it means you're just going to take 1.210 plus 1.223 plus 0.996 plus 1.223 plus 1.287. That gives you the sum of 5.939, but then we have to divide that by k, which is the number of samples, so divide by 5, and we get 1.1878, and again, if we round that to 3 decimal places, that's approximately 1.188. The test statistic then for one-way ANOVA compares our 2 estimates from the common population variance, sigma squared. The test statistic is denoted as F, named for the great statistician Ronald Fisher. So in this case, we take our 2 previous answers, which was n times S sub x bar squared, and then divide that by S sub p squared, so our 2 previous numbers that we boxed up there, and we're going to be dividing them to get our capital F. The null hypothesis and the test statistic assume all population means are equal, and under this condition, the F statistic will be nearly 1 because the numerator and denominator are both estimates of the same number, sigma squared. So we're going to first talk a little bit about F just to see if we can understand what our answer is about to tell us. So number 7, the numerator of the test statistic contains the variance of the sample means. Suppose the null hypothesis is false. Work with your group to decide whether this should cause the F test statistic to be greater than or less than 1. Give a reason for your decision. So when thinking about this, take a look at the paragraph just before number 7. If we have the null hypothesis assumes all population means are equal, it means under this condition, the F statistic will be nearly 1 because the numerator and denominator are both estimates of the same number. So, in number 7, they say, suppose the null hypothesis is false. So if the null hypothesis is false, that means at least one of the population means would be different, which would mean that that F statistic would be different from 1. So if there is a difference, you can think there's a greater difference between the samples, which means there's a greater variance between the samples. And in your F statistic above, variance between the samples is your numerator. So if that number in the numerator is greater, that means that the number for F would be greater than 1. So turning the page, what is the value of our F test statistic? So here we're just going to take our two previous answers. We had 8.659, and then we divide that by 1.188. You can already suspect that our numerator is greater, so we're going to get an F test statistic that is greater than 1. So 8.659 divided by 1.188, and we get approximately 7.289. To compute p-values, we obviously need to understand the distribution of such F statistics. Because the F statistic is a ratio of positive numbers, it is always positive. The distribution starts at 0 and is skewed to the right. The mode under the highest part of the graph is near 1. So F test statistics that are greater than 1 are essentially in the right tail. Number 9, add the F test statistic to the graph above. Then shade the region whose area is the p-value. If you notice here, there's 0 and 1, which would mean 2, 3, 4, 5, 6, 7. Our test statistic is even a little bit more than 7. So right here we could say there's F equal to 7.289. And if we wanted to shade the p-value, that would just be this little sliver that's under the graph. So here's a summary so far of what we've talked about. When the null hypothesis is false, the sample means should be very different, and their standard deviation S sub x bar will be large, causing the variance between the samples to be even larger. This will yield a large F test statistic and a small p-value in the right tail of the distribution of F statistics. This is why the F test is always a right-tailed test. There are two variances, or standard deviations, used in the F statistic, and each has its own degree of freedom. For the variance in the numerator, S sub x bar squared, the degrees of freedom are k minus 1. This is one less than the number of sample means. So numerator degrees of freedom, df sub 1, is k minus 1. For the pooled variance, the variance that we have in the denominator, the variance within the samples, we combine k sample variances, each with n minus 1 degrees of freedom. So in this case, the denominator degrees of freedom, df2, is equal to k, the number of samples, times n minus 1. We use technology to determine p-values for this F-test. One way to do this is using an online p-value calculator, such as the one found at the website below. For us, we are going to use our calculator, and the test that we're going to be looking for is just going to be called ANOVA. So first, number 10, what are the degrees of freedom for variance in the numerator of the test statistic? This is just what was described before, k minus 1. In our case, we have 5 samples. That's what k was. So that degree of freedom would be 4. For number 11, what are the degrees of freedom for variance in the denominator of the test statistic? That would be k times n minus 1, which is 5 times 7 minus 1, or 5 times 6, which is 30. And then number 12, here's where we need to use the ANOVA function. So I'm going to turn over to our calculator, and we can see how to use this. I'm going to start by going to the Stat button and Edit. And I want to put all of our data into these lists. So I have 5 lists here, L1, L2, L3, L4, L5. And those go along with the lists that we had for our treatments. So L1, list 1, that's the data that I had all the way before number 1 in our workbook for the placebo, the temperatures for those taking the placebo. Then list 2, that would be the temperatures for those taking aspirin. List 3 is the numbers for Anacin. List 4 is the numbers for Tylenol. And list 5 is the numbers for Bufferin. So I have those 5 columns of data entered in. So now that I have all of that entered, I'm going to press Stat again. Go over to Tests. And you want to go all the way to the bottom, which you could use the down arrow for that, but you could also use the up arrow. And you can see that ANOVA is the last test all the way at the bottom. So I'm going to click on Enter for ANOVA. And then here you have a parenthesis. You just need to type in the 5 lists that we're using. So list 1, so second and 1, and then comma, list 2, second and 2, and comma, and so forth. Second and 3 for list 3, comma, second and 4 for list 4, comma, and then second and 5 for list 5. Then close the parenthesis and then press Enter. And what you're about to see is a whole bunch of information, but we already have all of this information written down. So I just want to notice right here at the top, notice the F value. Capital F equals 7.287. If you go back to our answer on number 8, we had 7.289, which is very close to what we have here in the calculator. Why is the calculator slightly different? Because there wasn't any rounding in the calculator before this point. So notice right here, capital F we get for number 8 comes right from our calculator. So I'm going to write that down for number 12. F is 7.287. Then you can see that we have this lowercase p that's written there. What do you think that stands for? That's our p-value. So the p-value in this case, it says 3.172, but don't forget off to the right, there's the capital E -4, which means I have to take the decimal point and move it 4 spaces to the left. Which means we have 0.00037172, which is definitely a very small p-value. So that is our answer for number 12. And while we're here looking at this screen, there's a couple of other numbers that I want to point out. Notice DF equal to 4. That was the first degree of freedom. That was our answer for number 10. DF1 is what we said 4 was. If you use the down arrows, there's a second DF. DF2 is what we wrote for number 11, and that was 30. There's some other numbers that are written here, SS and MS, and some of those numbers we can go back and actually see what they dealt with. The first MS, the one that says 8.656, that was the answer to number 5. So I'm just going to make a little note in our workbook. MS1, that was the answer that we got for number 5. And then MS2, that was the answer that we got for number 6. So all of these previous calculations that seemed like a lot of work to do, we aren't going to have to do it. It's just entering in lists and doing this one calculator function, ANOVA, and we get all of those answers for free. The other numbers, the SS numbers, those will be important for the next section, 952. So now let's go back to our workbook and finish up this hypothesis test. So now we take our p-value and we draw our conclusions. Step 4, state a conclusion. As always, we reject the null hypothesis when the p-value is less than alpha. So first of all, number 13, what does the p-value tell you about the null and alternative hypothesis? So in our case, our p-value is 0.0003, which is definitely less than alpha, which is 1% or 0.01. So this tells us reject the null hypothesis. And it means that the data supports the alternative. So we reject the null hypothesis, the data supports the alternative hypothesis. Number 14, state a conclusion in the context of this problem. So we have data that supports our alternative hypothesis, which is the same thing as the claim that we had. So the evidence or data supports the claim that the mean body temperatures are different for the given treatments. And then to understand this conclusion a little bit more, number 15, is there a pain reliever that stands out as being particularly effective when it comes to lowering body temperature? So let's go back to some of our data, and what might help us with this are the confidence intervals. So first of all, why did we say that the evidence is showing that the mean body temperatures are different? The placebo is the one that stands out the most. Notice the mean for placebo is the highest out of all of them, and that confidence interval is the highest. The answer for number 15 is they want to know, is there a pain reliever that is effective when it comes to lowering body temperature? So in this case, which confidence interval seems to show a treatment giving lower body temperatures? That would be Tylenol, where you can see its lower bound on the confidence interval is the lowest out of all of them. So for number 15, we would say Tylenol. That's the one that works the best. And placebo is the least effective. We'll just make a note of that. By the way, the secret word for this lesson is Tylenol. So then finally, summarizing everything that we just saw, you need to know one-way analysis of variance, ANOVA, can be used to test for the equality of means from k different populations where k is greater than or equal to 3. So as a reminder, our null hypothesis is that all of the population means are equal, and then the alternative is at least one population mean is different. The assumptions of the test are that the populations are normal with equal variances, but these assumptions are not strict. Small departures from these assumptions still tend to yield good results. When all samples have a common size, n, the f-test statistic is the ratio of the variance between the samples, n times s sub x bar squared, and the variance within the samples, also known as the pooled variance, s sub p squared. That whole sentence is summarized in that formula. The degrees of freedom for the variance are in the numerator are df1 equal to k minus 1, where k is the number of samples, and the degrees of freedom for the variance in the denominator are df2 equal to capital N minus k, or as we saw before, k times lowercase n minus 1. The test is always right-tailed, and p-values need to be computed with technology such as the website below. For our purposes, we're just going to remember that we want to use stat, test, and ANOVA. That's all that we're going to need. In fact, we're going to do the exact same thing in the next lesson, 952.